Now we're going to look at the special case of uniform motion. So up to this point, we've looked at position, velocity, and acceleration. And we've said if you take the derivative of position with respect to time, you get the velocity. If you take the derivative of velocity with respect to time, you get the acceleration. Or if you integrate, you can go the other way. So this means if I give you any equation that represents position and ask you for velocity or acceleration, you should be comfortable solving that, or vice versa. So you should be able to move around from position, velocity, acceleration. You should know how to do that. But there is a situation when these equations become simpler, and instead of having to always take the integral, there's equations that we can just rely on when there's uniform motion. So what do I mean by uniform motion? So the first case is uniform velocity. So uniform velocity means the velocity is not changing. So uniform velocity means the velocity is not changing. And in mathematical notation, that means dv over dt is equal to 0, because the change with respect to time of velocity is equal to 0. So if we write out the same equations before where we were looking for position, so let's say I told you we have uniform velocity and I want to know what the position is, what would that integral look like? So we would have dx over dt is equal to velocity. We've looked at that before. If we bring the dt up, we have dx equals v dt. Now in order to get the position equation from this, we would integrate, right? That's what we were doing before. But now, because velocity is not changing, it means we can move this velocity outside of the integral. So we don't have to integrate velocity because it's not changing with time. So now, if we move the v outside, we would have the integral of dx is equal to v times the integral of dt. I'm just going to move this page up. When we perform this integral, we add our limits. We have x naught to x, and we have t naught to t. This integral reduces to x minus x naught is equal to v times t minus t naught. In this case, t naught, we'll assume t naught is 0 because it almost always is in these problems. And then we can rewrite this equation as x is equal to vt plus x naught. This equation here will apply for rectilinear motion uniform velocity. It's really important. This means that the velocity is the same no matter what t value you have for your equation. Now we're going to look at uniform acceleration. Can anybody guess how many equations we're looking at for uniform acceleration? How many equations should we be able to derive? We should be able to derive 3 equations because we have 3 equations for representing what the acceleration is. So we have acceleration is equal to dv over dt. We have acceleration is equal to d squared x over dt squared. And then we also have acceleration is equal to v dv over dx. So we can simplify all 3 of these equations to get equations for uniform acceleration. These ones also only apply to rectilinear motion. And they only apply when the acceleration is not changing. A very, very common mistake is that students assume uniform acceleration when it's not uniform. So I'm actually going to get you to pause the video here for a second, and I'd like you to derive the equation for uniform acceleration from a is equal to dv over dt. So derive an equation for how velocity will respond to a change in time with uniform acceleration. So now that you've done that, and I know that you've paused the video and derived this, I'll walk you through it. So it's exactly the same process as before. We bring our dt up. So now we have a dt is equal to dv. But because our acceleration is not changing, we can leave it outside of the integral. So we end up, and this goes from t naught equal to 0 to t, and v naught to v. So this ends up being a t is equal to v minus v naught. If we arrange this, we have velocity is equal to the acceleration times time minus the initial velocity. So this equation relates velocity, acceleration, and time. So there's nothing in here about position. So if the question gives us information or wants information about the position of the particle, this equation won't help us. So we need to derive another equation. So in this case, we'll say a is equal to d squared x over dt squared. This is the second acceleration equation that we derived previously. I strongly recommend you pause again and try to derive an equation that relates the position of the particle to the acceleration and the time. So now that you've given that a shot, I'll show you how to do it. So in this case, we rewrite the equation. We have acceleration is equal to d over dt times dx over dt. So all I've done is expand this term into two pieces here. And then what I'll do is I'll rewrite acceleration in terms of the change in velocity. So I'll say d over dt of velocity is equal to d over dt of dx over dt. Now, here we'll use a little bit of a trick. We derived an equation for velocity up here. So I'm going to plug this equation into here. I'll just move the screen up. So then we end up with d over dt of at plus v naught is equal to d over dt times dx over dt. And now, because we have a d over dt on both sides, we can cancel these out directly. Now what we're left with is an equation where we have a dx here and a dt, so we'll bring the dt over here to match where the time variable is. So we have at plus v naught times dt is equal to dx. And now we integrate both sides the same as before. So we'll go from t naught equals 0 to t and x naught to x. And now we're left with a t squared over 2 plus v naught t is equal to x minus x naught. If I rearrange this, we have x is equal to at squared over 2 plus v naught t plus x naught. This equation here relates position, velocity, acceleration, and time. For our third acceleration equation, I'm going to move this up again. We'll start off with acceleration is equal to v dv over dx. This one is pretty straightforward again. We bring the dx up here, so we have a times dx is equal to v dv. In this case, the acceleration is constant, so we can leave it outside of the integral. But the acceleration is constant, the velocity is not constant. So we need to include velocity inside the integral on this side. So what we're left with is from x naught to x for our limits, from v naught to v, we have a times x minus x naught is equal to v squared over 2 evaluated from v naught to v. so we end up with a times x minus x naught is equal to v squared over 2 minus v naught squared over 2. If we rearrange this equation, we end up with v squared is equal to v naught squared plus 2a times x minus x naught. Now this equation, we've got we've got velocity, we've got initial velocity, we've got acceleration and position, but this does not include time. So if the problem doesn't give us any information about the time, but we have information about the position and acceleration of the particle, we could still find the velocity. In this video, I'm just going to move this up. In this video, we derived four equations. If we have uniform velocity, we're looking at x is equal to vt plus x naught. And for uniform acceleration, we have v is equal to at plus v naught. We have x is equal to x naught plus v naught t plus 1/2 at squared. And we've got v squared is equal to v naught squared plus 2a times x minus x naught. Keep in mind that these only apply to uniform velocity or acceleration in rectilinear motion. And it's very common for students to use these equations when that velocity is not uniform or the acceleration is not uniform. So be very, very careful about when you're applying these equations. But if it is appropriate, it simplifies your life a lot.